The roar of four massive engines echoed across the runway as Japan's first heavy bomber, the Nakajima Shinzan, struggled to lift off from the 4200 FT concrete strip. With an empty weight of 44,313 LABs, it was 8,000 LABs, heavier than the American B-17 Flying Fortress. The test pilot fought sluggish controls as the colossal aircraft finally clawed into the sky, climbing at a mere 500 FT per minute, half the climb rate of an American bomber. Below, Chief Engineer Kenichi Matsumura watched through binoculars, his notebook filled with calculations that should have predicted this moment. Japan had bought the only Douglas DC-4E prototype in 1939 for $275,000, believing it would unlock America's aviation supremacy. After 2 years of reverse engineering and using the best materials Japan could muster, they aimed to create their own version of American excellence. But as the Shinzan disappeared into the haze, struggling to stay aloft, one harsh truth became clear. Simply copying American technology wasn't enough. Understanding the rationale behind its design was essential. On April 8, 1941, Matsumura stood at Oda Airfield, preparing to witness what the Imperial Japanese Navy believed would be their answer to American strategic bombing. The Shinzan, with its 4 powerful engines, sat at the end of the runway, its engines rumbling ominously. Matsumura had spent 18 months overseeing the development of the aircraft, driven by a singular obsession: Japan's need to strike at industrial targets over 2,000 miles away from their base. The B-17 Flying Fortress represented everything Japan lacked: reliable engines, defensive firepower, and critical operational range to strike at the heart of enemy territories. As Matsumura watched, Major Katsuaki Kira completed his pre-flight checklist in the Shinzan's cockpit. The bomber, 138 feet long, gleamed in the early light, its silver aluminum skin reflecting the sun. On paper, the specifications looked formidable: 4,000 kil of bomb capacity, 3,500 miles of range, and defensive armament designed to fend off intercepting fighters. The Navy had hailed it as Japan's war-winning aircraft, the weapon that would cripple American industry. However, Matsumura's engineering notebooks painted a different picture. The Shinzan's empty weight of 44,313 lbs was 8,000 lbs heavier than the B-17G, which weighed just 36,135 lbs without fuel or ordnance. This discrepancy contradicted everything Matsumura had learned in his 20 years as an engineer. The Shinzan's 4 mammary engines, each producing 1,970 horsepower, created a combined 7,480 horsepower to lift 62,600 lebs at maximum takeoff weight. But Matsumura quickly calculated that this only provided 120 horsepower per 1,000 lbs. Whereas the B-17 achieved 133 horsepower per 1,000 lbs with its Wright Cyclones, engines that had proven their reliability through countless combat missions over Europe. Major Kira released the brakes, and the Shinzan began its slow roll down the runway. The bomber's takeoff was sluggish, consuming 200 feet of concrete before lifting off, double the distance the B-17 required. The Shinzan climbed at a grudging pace, struggling to gain altitude at just 500 feet per minute, while the B-17 climbed at 900 feet per minute, eager to reach bombing altitude. Matsumura could see the pilot fighting the controls, which responded like they were submerged in thick oil, as the Shinzan struggled to maintain altitude as the aircraft disappeared into the haze. Matsumura fully understood the magnitude of Japan's error. 2 years earlier, Japan had bought the Douglas DC-4E prototype, convinced it was the key to unlocking American aviation dominance. The massive 4-engine airliner seemed perfect for military adaptation, with its 138-foot wingspan, all-metal construction, and tricycle landing gear. But the DC-4E had been rejected by American airlines, considered too complex and expensive for commercial service. Major airlines like United and Eastern Airlines had dismissed it as overbuilt, over-engineered, and unfit for profitable service. What Japan had thought was a symbol of American technological achievement was, in fact, one of America's most expensive failures. Matsumura's team had meticulously reverse-engineered every part of the DC-4E, assuming that replicating its design would give them the edge they needed. But they had missed the crucial point. Simply copying the design wasn't enough without understanding the reasoning behind it. American design philosophy prioritized raw power over efficiency. They reinforced structures that were already overbuilt, added defensive positions that increased weight without enhancing effectiveness, and installed engines that provided adequate power but lacked the reliability necessary for prolonged combat operations. The mammary radials failed every 50 flight hours, requiring complete overhauls that drained valuable materials and skilled labor. In contrast, Wright Cyclones in American bombers routinely operated for 400 hours between major maintenance. The irony was crushing. Japan had spent 2 years and millions of yen replicating an aircraft that Americans had abandoned as commercially unfeasible, only to make it even heavier and more complex in the name of military adaptation. Every calculation in Matsumura's notebooks confirmed what the morning's test flight had shown. The Shinzan was fundamentally flawed, a magnificent example of precise engineering applied to the wrong foundation. Radio static crackled from the control tower as Major Kira reported his position. 20 minutes into the flight, service ceiling tests would come later, but early indications suggested the Shinzan would struggle to reach 24,000 feet under combat conditions. B-17s routinely cruised between 25,000 and 30,000 feet, using altitude as their primary defense against intercepting fighters. The American bombers operated in an altitude range that Japanese fighters could hardly reach, making the sky itself a form of defense. As Matsumura walked back toward the engineering hangar, his mind already processing the implications of the morning's failure, it became clear Japan needed strategic bombers desperately. But copying American technology had proven insufficient. The purchase of the DC-4E had been based on the assumption that acquiring enemy hardware would automatically bring the enemy's capabilities. But capability wasn't in the blueprints. It was in the industrial philosophy that created them. American aircraft designers didn't just build planes. They built planes that could be mass-produced, maintained by minimally trained mechanics, and operated reliably by 20-year-old crew members. Japanese engineers built masterpieces that demanded constant attention from skilled craftsmen, aircraft that were technically advanced but operationally fragile. The Shinzan would never enter production. Even as Major Kira completed his test flight and prepared for landing, Matsumura knew that Japan's first attempt at copying American strategic bombing capability had failed before it even started. However, failure, Matsumura realized, might offer lessons that success could never provide. As spring arrived at Nakajima's Kisumi facility, there was a renewed sense of urgency driven by the Navy's unwavering conviction that Japan's strategic bomber program could still deliver victory. Despite the Shinzan's disappointing performance, Admiral Isoroku Yamamoto's staff issued new directives that bordered on the impossible. Develop a heavy bomber capable of reaching the American mainland within 18 months, or watch Japan's opportunity slip away. Matsumura found himself working 16-hour days, his engineering team swelling to over 200 specialists who'd been pulled from every major aircraft project across Japan. The Navy's faith in the Shinzan remained unshaken, based on specifications that looked impressive when typed onto official procurement documents. 4,000 kilos of bomb capacity, 3,500 miles of operational range, and defensive armament consisting of 4 20mm cannons and 12 7.7mm machine guns. On paper, the aircraft seemed capable of devastating American industrial targets from the Midwest to California. But Matsumura's flight test data painted a different, more troubling picture. The Shinzan's maximum speed of 261 mph made it vulnerable to any modern fighter aircraft, while its service ceiling of 24,450 ft left it exposed to interceptors attacking from above. American P-38 Lightnings, according to captured intelligence reports, could reach 39,000 ft and achieve speeds of over 400 mph in diving attacks. The engine reliability issues were even more devastating than the performance shortcomings. The mammary radials required complete overhauls every 50 flight hours, consuming aluminum alloy that Japan could ill afford. Each engine contained components that demanded Japan's most skilled workers, men who were urgently needed for Zero fighter production as the war spread across the Pacific. Worse, the engine's vibrations caused severe issues, loosening instruments, cracking fuel lines, and weakening airframe structures at an alarming rate. By contrast, Wright Cyclones in captured B-17s showed wear patterns consistent with 400 hours of operation between major maintenance. American engine design philosophy emphasized reliability over peak performance, accepting slightly lower power output in exchange for vastly improved operational availability. A B-17 squadron could maintain combat readiness for months, while the Shinzan bombers would spend more time in maintenance hangars than in combat. Matsumura's calculations confirmed that the Shinzan, like the DC-4E, was not the solution Japan had hoped for. The team had begun thoroughly examining Wright R-1820 engines salvaged from B-17s shot down over the Philippines, and the differences in manufacturing philosophy became immediately evident. American cylinders featured simpler cooling fin designs that could be mass-produced on automated machinery. In contrast, Japanese engines used complex cooling patterns that required hand finishing by skilled craftsmen. American connecting rods were forged from standardized steel alloys, while Japanese rods used exotic metals that enhanced performance but led to supply chain bottlenecks. The underlying issue went beyond individual components to the entire industrial approach. American aircraft manufacturers designed for mass production from the very beginning, creating aircraft that could be assembled by workers with minimal training using standardized tools and procedures. Japanese designers, on the other hand, optimized for performance and craftsmanship, building aircraft that needed skilled artisans at every stage of production. The result was bombers that performed excellently when new but degraded quickly under combat conditions, requiring constant attention from specialists who were increasingly difficult to replace. By the summer of 1941, the Shinzan program had consumed resources equivalent to the construction of 300 fighters, but had produced only 6 prototype bombers. Production rates that had seemed sufficient during peacetime planning proved catastrophically inadequate as the war expanded beyond anyone's initial projections. American factories were already producing B-17s at a rate of 20 aircraft per month from single production lines, with additional facilities planned to meet increasing military orders. The weight problem that had plagued the Shinzan since its first flight only worsened as more equipment was added. Armor protection for critical systems added 1,200 LABs, improved defensive armament contributed another 800 LABs, and self-sealing fuel tanks, essential for survivability over enemy territory, increased the empty weight by 1,500 LABs. Every modification that improved combat capability only worsened the aircraft's already marginal performance, creating a vicious cycle where survival enhancements made the bomber too slow to avoid the very threats they were meant to protect against. Matsumura's calculations revealed that a fully loaded Shinzan, carrying maximum fuel and ordnance, would struggle to maintain altitude if even one engine failed. Twin-engine flight characteristics were borderline dangerous, and single-engine performance made successful landing attempts highly uncertain. Intelligence reports suggested that B-17 crews routinely returned to base on just 2 engines, sometimes even managing to get home after losing half their power plants to enemy fire. The aluminum shortage that began affecting all Japanese aircraft production in late 1941 hit the Shinzan program particularly hard. Each bomber required 8 tons of aluminum alloy, compared to 5 tons for a Zero fighter and just 3 tons for a typical Army bomber. Japan's total aluminum production capacity could theoretically support 12 Shinzan bombers per month, but only if no other aircraft were being produced simultaneously. Wartime priorities meant that heavy bomber production had to compete with the fighter programs urgently needed for homeland defense. By 1943, American aluminum production was estimated to exceed 900,000 tons annually, while Japan's production peaked at just 142,000 tons in 1944, creating a resource gap that made large-scale bomber production impossible. Regardless of design efficiency, even if Matsumura's team had created the perfect aircraft, Japan simply lacked the industrial capacity to produce it in large enough numbers to matter strategically. The psychological impact on the engineering team became increasingly apparent as test flights continued to expose fundamental issues. Workers who had spent months perfecting individual components watched helplessly as their craftsmanship was rendered meaningless by systemic design flaws that could not be fixed with incremental improvements. The Shinzan required a complete redesign from the ground up, but Navy procurement schedules left no time for starting over. By autumn, Matsumura reached a conclusion he dared not express in official meetings. Japan was building the wrong aircraft, using the wrong methods for the wrong strategic situation. The Shinzan embodied everything Japanese engineering did well: precision manufacturing, attention to detail, and optimization of individual components. But it was applied to a mission that required exactly what Japanese industry did poorly: mass production, simplified maintenance, and design for reliability rather than perfection. The captured B-17E arrived at Nakajima's facility on a flatbed truck in March of 1942, its aluminum skin bearing scorch marks from the fighter attack that had forced it down in the Philippines. Matsumura stood beside the hangar doors as workers carefully maneuvered the intact bomber inside, feeling a mix of anticipation and professional dread. For 18 months, Matsumura's team had been reverse engineering the DC-4E prototype, assuming they understood the essence of American design philosophy. Now they would finally examine the real thing. The Flying Fortress appeared smaller than anticipated, with its wingspan of 103 ft seeming almost delicate compared to the Shinzan's massive 138 ft span. However, as Matsumura's inspection team began their detailed analysis, the true differences became apparent in ways that contradicted their assumptions about American engineering. The B-17's empty weight of 36,135 lbs was 8,000 lbs lighter than the Shinzan. Despite carrying similar defensive armament and fuel capacity, Matsumura personally supervised the engine removal process, closely observing as technicians carefully extracted the Wright R-1820 Cyclone radials that had powered the B-17 across thousands of miles of the Pacific. Each engine weighed 1,850 lbs and produced 200 horsepower at takeoff settings. In contrast, the Shinzan's mammary engines weighed 2,100 lbs each and produced 1,870 horsepower, creating an impressive power-to-weight ratio. However, when compared with American efficiency standards, it seemed less remarkable. The Wright Cyclones displayed wear patterns that spoke volumes about their operational reliability. Cylinder walls showed even scoring consistent with hundreds of flight hours, while connecting rod bearings displayed minimal degradation despite the obvious combat stress. The simplicity of the cooling system was especially striking. Straight fins were machined using automated equipment, rather than the complex curved patterns that the Japanese engineers had assumed were necessary for adequate heat dissipation. Disassembling the American engines revealed a manufacturing philosophy that challenged everything Matsumura had been taught about precision engineering. The tolerances were looser than the Japanese standards would ever accept, yet the engines operated more reliably than the mammary radials, which had been built to much tighter specifications. American designers had seemingly optimized for consistent performance, accepting slightly lower efficiency in favor of drastically improved maintainability. The differences in airframe construction were equally enlightening. The B-17's wing spars were made using aluminum extrusions that could be mass-produced in rolling mills, with reinforcements focused at high stress points rather than spread throughout the structure. Japanese engineers had constructed the Shinzan wings using complex forgings that required individual machining, creating parts that were theoretically superior but practically impossible to mass-produce. Matsumura spent hours examining the B-17's electrical systems, marveling at the standardization that allowed components to be replaced with minimal training. Wiring harnesses featured color-coded insulation and standardized connectors, eliminating guesswork during field maintenance. Control cables were routed through accessible channels with inspection plates at regular intervals, enabling quick identification and repair of issues. In contrast, the Shinzan's electrical systems required specialized knowledge for servicing, with custom connectors and hidden routing that made troubleshooting a time-consuming process. The defensive armament installation revealed another fundamental difference in approach. The B-17's gun positions were designed for quick installation and removal, using standardized mounts that could accommodate various weapon types depending on mission requirements. Ammunition feeds employed simple mechanical systems that rarely jammed, even during violent maneuvers. Japanese defensive installations, on the other hand, prioritized precision and firepower, with complex hydraulic systems that provided superior accuracy but required constant adjustments from skilled armorers. Flight control systems in the captured B-17 were operated by cables and pulleys, which seemed almost primitive compared to the Japanese hydraulic boost systems. Yet American pilots reported excellent handling characteristics under all conditions. The mechanical controls offered direct feedback, allowing pilots to sense impending stall conditions, while hydraulic systems often masked dangerous flight attitudes until recovery became impossible. Matsumura realized that simplicity was not a sign of inferior engineering, but rather evidence of a superior design philosophy. The fuel system design further emphasized American priorities. The B-17's tanks were constructed from simple aluminum sheets with rubber bladders that could be replaced in the field using basic tools. Self-sealing capabilities were achieved through rubber compounds that automatically sealed small punctures, offering protection without complex mechanisms that might fail under combat stress. In contrast, Japanese fuel systems used sophisticated pumps and valves for precise fuel management, but created multiple failure points that could leave aircraft stranded far from home bases. As his team compiled their analysis throughout the summer of 1942, Matsumura began to grasp the magnitude of Japan's strategic error. American engineers weren't merely building individual aircraft. They were designing production systems capable of manufacturing thousands of aircraft with workers possessing limited training. Every component was optimized for mass production, field maintenance, and operational reliability. Rather than peak performance or engineering perfection, the numbers revealed the story with heartbreaking clarity. B-17 production had reached 48 aircraft per month at Boeing's Seattle facility alone, with additional production lines set to be activated as military contracts expanded. Each bomber required approximately 15,000 man-hours to complete, compared to the 32,000 man-hours needed for a single Shinzan prototype. American workers could produce 3 B-17s in the time it took Japanese craftsmen to finish one heavy bomber. Material usage comparisons were equally sobering. A B-17 consumed 5.2 tons of aluminum alloy, while the Shinzan required 8.1 tons for comparable capabilities. American designers had eliminated unnecessary material through systematic analysis of stress distribution, creating structures that were strong enough to meet operational needs without adding excess weight that would degrade performance. Japanese engineers, however, built structures stronger than necessary, assuming that more strength was always better than optimizing the design. The maintenance philosophy differences became evident when examining the logbooks of the captured bombers, which had been recovered intact from the crash site. B-17 squadrons performed scheduled maintenance using standardized procedures that any trained mechanic could carry out in the field. Engine changes took just 6 hours with common tools, while hydraulic system repairs required only basic mechanical knowledge. Maintenance on the Shinzan, however, demanded specialists who understood the unique characteristics of each aircraft, making squadron-level repairs impossible under combat conditions. Most revealing was the American approach to battle damage repair. B-17s were designed to fail in a controlled manner, with damage concentrated at specific points that could be patched using field expedients. Aluminum skin panels could be replaced with sections cut from other aircraft, and structural repairs could use standard aluminum angle stock readily available from any industrial supplier. In contrast, Japanese aircraft required custom-made parts, manufactured to precise specifications, making field repairs impossible and forcing damaged aircraft to remain out of service for long periods. By October 1942, Matsumura had reached a conclusion that would completely reshape Japan's approach to strategic bomber development. The B-17 wasn't superior because of advanced technology or exotic materials. It was superior because American engineers had solved the right problem. Instead of creating the perfect bomber, they built one that could be manufactured, maintained, and operated by ordinary people in extraordinary circumstances. The path forward was clear, though daunting. Japan needed to abandon the Shinzan program and start from scratch, embracing American design philosophy as the foundation. But with 18 months of the Pacific War already past, time was running out for such a fundamental shift. On September 14, 1943, a telegram arrived from Imperial Navy headquarters at Nakajima's Kisumi facility, outlining specifications that seemed more aspirational than practical. Matsumura read the requirements twice before placing the document on his drafting table, realizing that Admiral Yamamoto's staff had essentially ordered his team to defy the laws of physics within an 18-month deadline. The specifications included a maximum speed of 370 km/h, faster than any existing heavy bomber, a service ceiling of 33,000 ft, high enough to operate above most intercepting fighters, and a range of 4,600 miles with a reduced bomb load, sufficient to reach the American West Coast and return. The bomb capacity was to be 8,800 lbs, enough to devastate industrial targets. The specifications read like a wish list written by men who had never considered power-to-weight ratios or aluminum allocation requirements. However, Matsumura had spent 18 months studying captured B-17s, and the insights gained from American engineering philosophy had crystallized into a revolutionary idea. Japan's fundamental mistake had been copying American hardware without understanding American methodology. The new bomber, designated GN Renzan, or Mountain Range, would completely abandon the DC-4E template and adopt the design principles that made American aircraft successful. In the autumn of 1943, working sessions stretched well past midnight as Matsumura's team discarded every assumption that had guided Japanese aircraft development since the 1930s. Traditional Japanese engineering emphasized individual craftsmanship and component optimization, resulting in technologically impressive aircraft that were manufacturing nightmares. American engineering, on the other hand, focused on systematic integration and production efficiency, creating aircraft that were good enough to be built by the thousands. The G8N design that emerged from these sessions looked nothing like previous Japanese bombers. Clean lines replaced complex curves. A single vertical stabilizer replaced the twin-tail configuration that had plagued the Shinzan's directional stability. Mid-mounted wings provided structural efficiency while improving maintenance access. Every component was designed for reliability first, performance second, and ease of manufacturing third, reversing traditional Japanese aircraft development priorities. The power plant selection proved critical to the program's success. Instead of adapting existing engines, Matsumura convinced Navy procurement to fund the development of the Nakajima NK9KL Homar engine. The Homar engine, specifically designed for the G8N mission, was a groundbreaking achievement. Each engine was capable of producing 2,000 horsepower at military power settings, providing a total of 8,000 horsepower to lift an aircraft designed to weigh 38,360 lbs empty. This power-to-weight ratio finally aligned with American standards while exceeding American performance expectations. The Homar engines incorporated lessons learned from the Wright Cyclone teardowns, focusing on operational reliability rather than peak performance. The cylinder cooling fins featured simplified designs that could be mass-produced, while internal components were manufactured to tolerances that balanced precision with production speed. Supercharging systems were optimized for high-altitude operations, ensuring full power output at altitudes where intercepting fighters would struggle to keep up. Airframe construction abandoned. The complex forgings and custom machining that had made the Shinzan prohibitively expensive to manufacture. The G8N's wing spars used aluminum extrusions, which could be produced on standard rolling mills, with reinforcement concentrated at high stress points rather than distributed throughout the entire structure. The skin panels were designed for easy replacement using common shop tools, enabling battle damage repair under field conditions. The electrical system design was based on hard-earned understanding of combat maintenance requirements. Standardized connectors and color-coded wiring eliminated guesswork during repairs, while accessible routing allowed mechanics to quickly trace and fix issues. Power distribution relied on proven, American-style bus systems instead of the complex switching networks that had made Shinzan electrical repairs a specialist task. Requiring days of troubleshooting, fuel system design prioritized survivability while ensuring ease of maintenance. Self-sealing tanks used rubber bladders that could be replaced by squadron-level mechanics, while fuel pumps and valves were positioned for easy access during scheduled maintenance. The system allowed precise fuel management for long-range missions, while avoiding the complex automation that had introduced multiple failure points in earlier designs. Defensive armament placement struck a balance between firepower and structural integrity, avoiding the weight penalties that had plagued previous Japanese bombers. Gun positions used standardized mounts that could accommodate different weapon types, while ammunition feeds relied on mechanical systems that functioned reliably during violent maneuvers. The installation provided comprehensive coverage without adding drag or weight that would compromise flight performance. The first G8N prototype rolled out of Nakajima's final assembly hangar on August 23, 1944, its silver aluminum skin gleaming under work lights that had burned continuously for 3 months. Matsumura personally oversaw the pre-flight inspection, checking systems that represented 4 years of accumulated knowledge about what made aircraft successful under combat conditions. Test pilot Captain Tishi Shirani completed the first flight on October 23, 1944, reporting handling characteristics that exceeded all expectations. A maximum speed of 368 mph at 26,245 ft validated the design calculations, confirming that the aircraft could match American-level performance despite Japan's manufacturing limitations. Service ceiling tests showed the aircraft could operate at 33,465 FAT, far above the altitude range, where most intercepting fighters could maintain effectiveness. Range testing also proved impressive, with a maximum distance of 4,639 miles demonstrated during carefully monitored fuel consumption flights. The GE-10 could reach targets on the American West Coast and return to bases in the Mariana Islands, finally providing Japan with the strategic bombing capability that had been promised since the planning for Pearl Harbor. However, as the third prototype completed acceptance trials at Koizumi Airfield in early 1945, the strategic situation that had justified the G-8N program was collapsing beyond repair. American B-29 superfortresses were systematically obliterating Japanese industrial capacity, while carrier-based aircraft operated freely over the home islands. The aluminum needed for G-8N production was being diverted to defensive fighter programs that offered more immediate protection against the bombing campaign, which was reducing Japanese cities to rubble. Only 4 G-8N prototypes would be completed before Japan's surrender brought the program to a permanent halt. The aircraft that had finally solved Japan's strategic bomber problem arrived too late to influence the war's outcome. A masterpiece of engineering rendered irrelevant by industrial realities that no amount of technical brilliance could overcome. Matsumura watched the 4th prototype taxi to its parking position on August 10, 1945, knowing that American technical teams would soon arrive to study what Japanese engineering could accomplish when freed from the constraints of copying foreign designs. The GE-10 represented everything Japan had learned about building aircraft the right way. But the time it took to learn the right way was too long for it to matter strategically. The surrender announcement reached Nakajima's Kisumi facility at noon on August 15, 1945, crackling through radio speakers with static, marking the end of a program that had come too late to change the course of the war. As Emperor Hirohito's voice echoed across Japan, informing the nation that the war had ended, Genichi Matsumura stood in the engineering hangar beside the 4th G-8N prototype, watching his team of 200 specialists come to terms with the reality that 4 years of intensive development had culminated in Japan's unconditional defeat. Outside the hangar, American B-29 superfortresses continued their relentless destruction of Japanese industrial capacity, their contrails visible at altitudes that the G-8N could theoretically reach but would never operationally challenge. The irony was complete. Japan had finally developed a strategic bomber capable of matching American performance, only for American strategic bombers to obliterate Japan's ability to manufacture aircraft in meaningful quantities. The numbers that defined the program's ultimate failure were etched into Matsumura's mind with mathematical precision. 4 G-8N prototypes were completed, compared to 12,731 B-17 flying fortresses built by American factories. 4 aircraft, representing the pinnacle of Japanese engineering achievement, versus an American production line that delivered more bombers in a single month than Japan had built in 4 years of concentrated effort. American technical intelligence teams arrived at Kisumi on September 3, 1945. Led by Colonel Harold Watson of the Army Air Force's Technical Intelligence Unit. Matsumura personally guided the examination of the G-8N prototypes, explaining design decisions and performance characteristics to American engineers who approached the aircraft with professional curiosity rather than triumph. The captured German and Japanese aircraft they were documenting were technological marvels that arrived too late to influence the war's outcome. Colonel Watson's assessment, recorded in technical reports that would remain classified for decades, acknowledged the G-10's impressive capabilities while highlighting the industrial limitations that doomed the program. The maximum speed of 368 mph exceeded early B-29 performance figures, and the service ceiling of 33,465 ft matched American heavy bomber standards. The G-10's range capability of 4,600 miles would have allowed strikes against the continental United States from bases in the Marshall Islands. But the performance specifications told only part of the story. Watson's team calculated that manufacturing a single G-10 required approximately 42,000 man-hours of skilled labor, compared to 18,000 man-hours for a B-29 Superfortress built on Boeing's automated production lines. Japanese craftsmanship produced aircraft that were technically superior in individual components. But American mass production created aircraft that were strategically decisive through sheer numerical superiority. The material consumption analysis revealed even starker contrasts. Each G-10 prototype consumed 8.7 tons of aluminum alloy, while American heavy bombers averaged 6.2 tons through systematic optimization of structural design. Japan's total aluminum production in 1944 peaked at 142,000 tons, theoretically sufficient to build 16,000 G-10 bombers if no other aircraft were manufactured simultaneously. In contrast, American aluminum production in 1943 exceeded 920,000 tons, supporting the simultaneous production of fighters, bombers, transport aircraft, and civilian goods without resource allocation conflicts. Matsumura found himself explaining to American interrogators the philosophical differences that had shaped Japanese aircraft development throughout the war. Traditional Japanese engineering emphasized perfection of individual components, creating aircraft that were marvels of precision manufacturing but nightmares of production complexity. American engineering emphasized integration of adequate components into effective systems, creating aircraft that could be manufactured by workers with minimal training using standardized procedures. The engine development comparison proved particularly illuminating for American technical teams studying lessons from the Pacific War. The NK-9KL Homar radials in the G-10 generated 2,000 horsepower each, through supercharging systems that represented cutting-edge Japanese technology but required complete overhauls every 120 flight hours due to metallurgical limitations in high-stress components. The Wright R-3350 Cyclones in the B-29 produced 2,200 horsepower while operating for 400 hours between major maintenance, thanks to systematic reliability engineering that prioritized operational availability over peak performance. Manufacturing philosophy differences extended to every aspect of aircraft production. G-10 wing spars were machined from solid aluminum billets using precision tooling, requiring hours of setup time for each component. B-29 wing spars were assembled from aluminum extrusions and sheet metal stampings, mass-produced using automated machinery operated by semi-skilled workers. Japanese methods produced structurally superior components, but American methods produced adequate components in quantities that overwhelmed any performance advantages. The maintenance requirements analysis revealed operational realities that had been invisible during peacetime development. G-10 systems required specialized tools and trained mechanics for routine maintenance, making squadron-level repairs impossible under combat conditions. B-29 systems were designed for maintenance by mechanics, with basic training using common tools available at any forward airfield. A damaged Superfortress could be returned to combat readiness in hours, while a damaged G-10 would require weeks of specialized repair work at major maintenance facilities. By October of 1945, American technical teams had completed their documentation of Japanese aircraft development programs and reached conclusions that would influence post-war military procurement for decades. Technical excellence without industrial capacity was strategically meaningless. The most sophisticated aircraft in the world could not compensate for fundamental limitations in manufacturing capability and resource allocation. Matsumura's final interview with Colonel Watson took place beside the fourth G-8N prototype on November 8, 1945, as American transport crews prepared to ship the aircraft to Wright Field for detailed analysis. The conversation focused not on technical specifications, but on the systemic factors that had determined the war's outcome, despite Japan's achievements in individual aircraft performance. The devastating arithmetic of industrial warfare had rendered engineering excellence irrelevant. More B-17 flying fortresses had been shot down over Germany, 4,150 aircraft, than Japan had built of all heavy bombers combined throughout the entire war. American factories replaced combat losses faster than Japanese factories could produce new aircraft, creating a mathematical impossibility that no amount of technical sophistication could overcome. Watson's final assessment, recorded in classified reports that would shape American understanding of industrial warfare for the Cold War era, emphasized lessons that extended far beyond aircraft development. Victory did not belong to nations that built the best weapons, but to nations that built adequate weapons in overwhelming quantities. The G-8N represented everything that Japanese engineering could achieve when freed from resource constraints. But resource constraints were the fundamental reality of modern warfare. Matsumura watched the fourth prototype disappear into the cargo hold of an American transport aircraft, understanding that his team's greatest achievement would become a museum exhibit rather than an operational weapon. 4 years of intensive development had produced an aircraft that could have changed the war's trajectory if manufactured in quantities that Japan was never capable of achieving. The lesson, learned too late, was simple. Manufacturing capacity, not technical brilliance, determines the outcome of war.